This is Stephanie from statisticshowto.com. This video is a brief introduction to chi-square. There are two types of chi-square tests. Both use the chi-square statistic and distribution for different purposes. A chi-square goodness of fit test determines if sample data matches a population. It fits a single categorical variable to a distribution. A chi-square test for independence compares two variables in a contingency table to see if they are related. In a more general sense, it tests to see whether distributions of categorical variables differ from each other, or if they are possibly related. The goodness of fit test is used to test if sample data fits a distribution from a certain population. In other words, it tells you if your sample data represents the data you would expect to find in the actual population. For example, you might survey 1,000 artists and ask them what zodiac sign they belong to. You would expect them to be evenly distributed across the 12 zodiac signs. But perhaps not. There might be more Aquarians or Capricorns. The chi-square test can help you test this theory. Two potential disadvantages of chi-square. The chi-square test can only be used for data put into classes, that is, bins. If you have non-bin data, you'll need to make a frequency table or a histogram before performing the test. Another disadvantage of the chi-square test is that it requires a sufficient sample size in order for the chi-square approximation to be valid. Here's the formula for the chi-square statistic you would use for goodness of fit. The subscript C is the degrees of freedom, O is your observed value, and E is your expected value. The summation symbol means that you'll have to perform a calculation for every single data item in your data set. As you can probably imagine, the calculations can get very lengthy and tedious. If you do need to calculate it by hand, in the next video, I'll walk you through the steps. For the chi-square test for independence, the main difference is that you'll be summing over positions in a contingency table instead of over categories. A low value for chi-square means there is a high correlation between your two sets of data. In theory, if your observed and expected values were equal, that is no difference, then the chi-square would be 0. That's an event that's unlikely to happen in real life. Deciding whether a chi-square statistic is large enough to indicate a significant difference isn't as easy as it seems. It would be nice if we could say a chi-square statistic greater than 10 means a difference, but unfortunately that isn't the case. You could take your calculated chi-square value and compare it to a critical value from a chi-square table. If the chi-square value is more than the critical value, then there is a significant difference. You could also use a p-value. First, state the null hypothesis and the alternate hypothesis. Then generate a chi-square curve for your results along with a p-value. Small p-values under about 0.05 usually indicate that a difference is significant or small enough. The null hypothesis for the chi-square assumes there is no significant difference between observed and expected values. The alternate hypothesis assumes there is a difference. Thanks for checking in, and I'll see you in the next video.